Hello everyone. So in this video, I will discuss system surrounding. I will define the control volume, control surface, and we will understand their utilities. And thereafter, I will discuss the Reynolds Transport Theorem, and which is basically the way we relate the changes in a system to a changes in control volume. So control volume approach is very much relevant in fluid mechanics, which basically helps in deriving all those fundamental law of mechanics, solid mechanics, into fluid mechanics. So in solid mechanics, for example, conservation of mass, Newton's second law, and then momentum, and then energy equation of thermodynamics law. All those things can be derived and can be used to understand basically fluid mechanics. So using then thereafter then in RTT, after understanding RTT, I will use the RTT to derive the conservation of mass, and then derive the Newton's second law, and later on the complete Navier-Stokes equation can be derived, and I will discuss the derivation of Bernoulli equation as well before coming to the Navier-Stokes equation. So stay tuned. I will then close my video and then continue with the derivation and discussion. Okay. All right. As I was saying, we am going to start with system. So when we say system, when we consider a fixed quantity of matter, okay, a fixed quantity of matter, then we say a system is a fixed quantity of matter. Okay, now of course it is going to have a boundary, right? So whenever we, let's say we consider this as our system, hang on, just when we consider this as our system, then it has certain boundary, right? So whatever mass that I'm considering here, I'm going to I define it as a system, and whatever is outside here, whatever it is remaining other than this, I should have used other color, fine. So whatever is other than outside of this boundary, okay, outside of this boundary, that is surrounding for us. Okay, fine. Now this, why am I acknowledging this boundary? It would be clear when I will be discussing the RTT, Reynolds Transport Theorem. Okay, now let's come to the control volume. So tell me one thing, when I considered system, two things you must understand here. One is any change is going to happen here inside, that is going to be like in change inside this system that I have considered, right? Maybe flux change, energy change. It is going to have a, what I'm trying to say is changes inside this boundary. Okay, let's say flux change with time. Okay, second important thing is nothing is crossing this boundary. Okay, nothing is going inside this system and nothing is going outside this system. Okay, so that means there's like, that's how the mass is fixed, right? No mass can enter or leave. Okay, that's how we are defining the system. Okay, all right. So when we say no mass can enter or leave, basically we are talking about closed system. Okay, so in fluid mechanics context, this is what we are going to consider. Okay, now there are other types of system that you understand in thermodynamics, like closed system, open system, and then completely like isolated system. So when we will discuss further, you will understand what I'm talking about. Okay, for the context, we are going to consider this no mass can enter or leave in the context of course, RTT. Okay, now when we say control volume, okay, now how do we define a control volume? So when we talk about control volume, it is basically, let's say I'm considering a, so I'm building so that it will be helpful later on. Let's say control volume is a set of, is a region in space from which I'm writing it in like my own language. So from which flow of matter or energy can take place. Okay, fine. So let me just draw this. So if I'm considering this region, okay, so this red and here blue, consider them same. So okay, so this is the control volume. Now it is going to be fixed in space, right? Region, it's a fixed region, the fixed region. Okay, fixed region, but any matter it can flow, I mean property basically, it can be mass, it can be energy, temperature, pressure, okay, enthalpy, heat, they can cross the boundary. So another thing I was talking about is control surface. Control surface. So what is control surface? The boundary of the control volume. Okay, I'm going to denote them as a CV and CS. Okay, so this boundary of the control volume is control surface, and where this change or flow of matter or property occurring, this is occurring through control surface. Okay, now I'm going to come to the RTT. Okay, RTT, Reynolds Transport Theorem. So what is it? Reynolds Transport Theorem basically a mathematical equation, okay, which uses integration and differentiation, a mathematical equation to relate changes in system to changes in control volume. Okay, so this is what basically if it in a crude way, this is how, this is what it does. Okay, so now I'm going to consider this again. Okay, so my control volume is going to be very simple to understand this Reynolds transport theorem. Okay, by the way, changes of what? So okay, I forgot, I should add changes in system, changes of what? Changes of a property. Okay, property could be, it could be mass, what else, energy, what else, enthalpy, maybe small h, but in fluid mechanics h is the pressure head or something, or potential head. So enthalpy and heat. Okay, something like this. Okay, now let's start that expression. So let's assume uh, simple pipe flow. Okay, you can have a arbitrary control volume and try to derive this RTT, but it would be good. I will derive the general form also. I will discuss the general form of RTT as well. Don't worry. Just to begin with, I'm choosing this. So this is, let's say we consider control volume. Okay, and so all these three things you have to keep in mind: system and control volume and control surface. Okay, so RTT, what it does, you have to keep that in mind also. It relates system with, it relates system with control volume. So what you have to do is you have to relate system with control volume, changes of a parameter in a system with control volume. So what I'm going to just explain it in a bit different way. What should I do? Okay, let me say this, there is going to be flow, this is a pipe flow, right? Now flow is going to happen. I have considered this control volume. Now let me say for a fixed point of time, this was my system. Okay, and what system is? Fixed matter, fixed quantity of mass, right? This is my system. of course with the same boundary. So what I'm trying to say is CV and system, imagine for them to coincide. Okay. All right. So CV, control volume and system are coincident at t equal to 0. And I'm assuming what I have what I'm what I've done is, let's say the fluid inside this control volume and control system at t equal to 0 are colored with a yellow dye. Okay, but remaining fluid, okay, this is, I cannot choose green, I can choose, let's say, okay, remaining fluid is of this color. Okay, fine. Now system and control volume at equal to 0, they are coinciding. So now with time I want to write the equation RTT for a parameter B. Okay, now I will define an intensive property which is beta, B by mass M. Okay, beta. So in the system, what is the change of this parameter B? B could be anything, like I said, mass, energy, enthalpy, heat. Okay, so dB system, or you can write differently little bit, dt for system. Okay, now you want to relate it with control volume. So if I consider property B, with time its change is dB by dt for a system. But what happens to control volume? Like I said, let me go back to the control volume. What was important here? It's a fixed region in space from which flow of matter or energy can take place. Okay, so flow of matter and energy can take place. Now what we do here is, system can be related to control volume. Now I'm talking about some time t equal to t. Okay, what would have happened? Okay, fluid may have crossed this boundary. So because by definition of control volume, fluid can cross, fluid any matter, right, fluid or matter can cross the control volume, cross the control surface. There may be some source or sink. Okay, so I recall one more term here, what I was struggling to say, that there could be source or sink to change in a system. Okay, so fine, you, if you go back and you understand, then you can think of it again. So in control volume, what would be happening? First of all, changes inside the control volume. Okay, I'm not considering what fluid has crossed the control surface, I'm only considering changes inside the control volume, plus crossing of crossing through control surface. Okay, this is what we have to consider. So changes inside the control volume, we define it as rate of change, by the way, rate of change. So we define as d by dt control volume rho into beta into t volume. So this v and cross, this is volume. Okay, and beta is intensive property, this. Okay, and this rho, I think I'm right, b by mass and mass upon volume. Take it. All right, and then what would be the property that is crossing through the control surface? Okay, now if imagine which property I'm talking about, crossing of fluid, right? So at some time t equal to t, what would have happened? Some of this blue color fluid would have entered here. Wait, okay, let me make it again just to make it clear. It will take some time, but it will be right. Green. I'm making this control volume scenario at t equal to t. Fine. So what would have happened? Some of the fluid would have crossed out, but I'm considering what system. I cannot consider other fluid. I'm only considering this yellow color fluid. Okay, and then some of the blue color fluid would have entered. Okay, see, this is not going to be straight. Turbulence is there, more mixing, and a lot of other things. I'm just simplifying it, and then fluid will start from here. Okay, so what would have happened? This pipe can extend, pipe you can extend. Okay, so this is the scenario at t equal to t. Okay, now to take this effect of this crossing of matter through the control surface, what would be this? This is basically control surface beta rho and this velocity, basically v in. So let me say this is v in and this is v out. Okay, so if you want to focus on only yellow color fluid, what will you consider? You will add to this control. In addition to this, you want to consider this yellow color fluid that has crossed v out into dA. Okay, or to put it differently here, yeah, v into dA, this is what is going out. So to be precise, you can write it like this. Okay, out, how much it is going. Okay, fine. And will you consider this fluid, this blue fluid? No. What has come in, you don't care about that, so that part you have to remove. Control surface beta rho v dot dA in. Okay, so this is your Reynolds transport theorem. Let me zoom in little bit. I hope it is clear. So I'm going to write it again, dB by dt system. So how did you relate? System change in property of B in the system is equal to change in property of B inside the control volume plus the property that has crossed out from the control surface that you must consider, because you want to focus on a system and system meaning same matter. You have to focus on the yellow color fluid. Okay, so whatever yellow color fluid would have crossed the control surface, you have to consider in minus whatever. So whatever this. So when you consider this another side of it, when you consider this control volume, you would have considered this blue color fluid also, change in control volume. That is why you have to subtract it. Okay, you don't want to focus on this, so you subtract whatever has come inside the control volume. Okay, so if you want to write it in a compact manner, you can further write dB by dt system is equal to d by dt control volume rho beta and dV plus. Now I took a very simple pipe flow right here. Direction of velocity and vector, see, this area vector, they are same basically. If you take here, what would be area vector? A unit vector along the area. This is that velocity is also this v out, and at the inlet this is going to be n cap and this is going to be v. So when you have some arbitrary shape of control volume and you just consider this area. Okay, when you consider this area and its normal vector, you know that is along this n cap and velocity vector is this, then you always consider velocity vector in the direction of this unit vector. Okay, and what would be that? V dot n cap. Okay, now you can combine these two, out minus in, mathematically at this. So tell me, what would be v dot n at the inlet? Minus b, isn't it? Because they are at 180 degree, they are opposite, right? Anti-parallel to each other. And what would be v dot n at the out? They would be zero, like angle between them are zero, they are parallel, so it would be positive v. So if I write them together, beta, wait, let me write with the same color. If I write them rho beta and v dot n cap into dA. Tell me, at the inlet v dot n is negative, so inlet you will subtract. At the outlet this is positive, so that you will add. So this is your Reynolds transport theorem. Okay, and we will use it to derive the several equations. For example, conservation of mass, which we often don't care in solid mechanics. Okay, 20 minutes video is already there. Let me quickly derive the conservation of mass in fluid mechanics. Okay, tell me one thing, when we talk about conservation of mass equation in fluid mechanics, conservation of mass in, conservation of mass, we are in fluid mechanics, fine. So what is this B property? B is m, right? And what becomes beta? M upon mass. It was intensity property, it becomes 1. Can we not put it here quickly? If we do that, what will I get here? dm by dt system, and mass is conserved, right? So this will not change. dm by dt is 0. And if you are converting it, changing it into this control volume, what will happen? Cv rho, by the way, here rho can change, beta can change with time and space. That's why integration is there. You have to consider all those factors. So we will be taking one of those one by one. Okay, beta is 1, so here what you will get, rho into dv plus control surface rho beta. Okay, beta is 1, and here v dot n cap into dA. Okay, now if it is a steady state, okay, then what will happen? There is no change inside this. Okay, even before that you can take this this d by dt inside. Okay, let me just do one more step, then we can jump. 0 is equal to control volume partial rho by partial t into dv. Rho can be a function of space and time also, that's why I have taken this partial derivative, right? Plus cs control surface rho v dot n cap into dA. Fine. So here when we talk about steady state, then there is no change in control volume. What will we have? Control surface v dot n cap into dA is equal to 0. Okay, now if you can simplify, let's say for pipe flow, in whenever we talk about rho, let's say at the inlet velocity is v1 and area is a1. Okay, and you integrate, right? dA is a small area, when you'll integrate you'll find the complete area. So let me erase this. So integration, by the way, okay, before I remove the integration, the factor is we have to consider fluid is incompressible. Okay, if incompressible, this density thing can come out of the integration, and when you will integrate v dot n cap dA, this is what you will get, right? v1 a1 but minus, right? This is at the inlet because v dot n is negative, plus v2 a2 at the outlet. 2 I am considering outlet. Okay, and 1 is inlet where this v dot n is negative, equal to 0. So what you got? v1 a1, the flow rate v1 a1 is equal to v2 a2. Fine. So or if it is at the inlet rho 1 is there, at the outlet rho 2 is there, but you know that rho 1 is constant at the inlet and rho 2 is constant at the outlet, so you can have rho 1 a1 b1 equal to rho 2 a2 b2. Okay, so that you can also do. So this is our continuity equation that we talk about, and this is our okay, yeah, that how you came across by using conservation of mass by using RTT. So I will use RTT to derive Bernoulli equation and Newton's second law in coming classes, coming videos. Okay, thank you so much for watching the video, and do subscribe to the channel for more such videos, and let me know your feedback, and thank you.